I will introduce very briefly the fifth assessment report of the Intergovernmental Panel on Climate Change. Working Group 1 has assessed the physical basis of climate change, and we will show in very simple terms what's the content of the summary for policymakers. There are basically three messages. The first one, warming in the climate system is unequivocal, as is demonstrated by millions of observations. The second message is human interference with the climate system is clear. That means that we know why the planet is changing. The cause is the increase of atmospheric greenhouse gases. And the third message is that limiting climate change requires sustained and substantial reductions in greenhouse gas emissions. Good morning, everybody. Thank you very much for giving me the opportunity to explain to you directly what the content of our first installment of the fifth assessment report of the Intergovernmental Panel on Climate Change actually is. I say it's the first installment because a couple of weeks ago, working groups 2 and 3 have also made their contribution and had their approval plenaries, and therefore all three reports are now available. But this first report was prepared by Working Group 1, the physical science basis, and probably speaks most directly to us here as a geoscience community. It's not myself who's giving this talk only, but I'm giving that on behalf of 259 colleagues who have worked for over 4 years on this report. So this is really a large community and collective effort which has led to this new assessment. The assessment itself consists of 14 chapters and an atlas. We'll give you an example of a few of the pieces of content. Overall, it's more than 1 million words, and I can tell you if you purchase the hard copy of the book, it's 4.2 kilograms in mass. So it's really a massive document, but everything is also available on the internet, and I've also brought with me a few copies of a CD, which we are welcome here to pick up at the break. Now, nobody would read 1 million words, and that's why we, in particular for the policymakers, those who have to take decisions, we have written a summary, and that summary contains about 14,000 words. Now, 14,000 words is a little brochure of 30 pages. And one of the most often raised criticism in the past assessment, which was published in 2007, was that you guys are writing far too complicated, it's too long, and couldn't you do something more comprehensive, more concise, more crisp? And so we really took a lot of time and a lot of effort to have a further distillation process of these 14,000 words. And we now come up with key summary for policy makers' messages, so-called headline statements. There are 19 of those, and they print on less than 2 pages. So I can now stand in front of everybody without being embarrassed and blushing and say, there is no more excuse for a policymaker not to have time to read our main messages, and there is no excuse not to understand them, because they are written in very simple and plain English with no jargon. They are short and quotable, and the best measure for that is that many of these messages have been taken over by the media without any change. I will make you a few examples. This is the big group that we were very fortunate to motivate to work with us for more than 3 years, very hard work in which they have looked at more than 9,000 publications to assess them, to summarize them, and to extract from that the status of knowledge on anthropogenic climate change. This is not the first assessment. As we know, IPCC was founded in 1988 in preparation of the Rio conference in 1992. And just 2 years before that legendary conference, the first assessment report was published, made available to inform the policymakers about this problem and what the scientists know about it. But since then, 5 reports have appeared, with the latest one, of which I'm going to show you a few of the highlights. Our report is organized along 3 pillars. The first pillar, observations, the second pillar, understanding, and the third pillar, projections. Now, this is the world as it's presenting us today. You see here the changes in surface temperature, annual mean surface temperature, expressed as the change in the past 112 years, calculated from linear trends based on millions of data points around the world. And you see that the message is clear. Most areas exhibit a clear warming. The warming has a regional expression. It is enhanced over continents. But we also need to be very clear. There are quite a few white spots on this planet, areas where we don't have sufficient material in terms of observations to make a statement on the changes of the past 112 years, in particular in the southern hemisphere, and with what is more disturbing also in the Arctic region, we have basically not sufficiently high quality data. So this is a problem, and it's a problem that is also impacting some very up-to-date questions that we try to investigate today. But nevertheless, looking at this, we could make one of the very simple headline statements, which is actually a repetition of a headline statement that was already produced in 2007 at the 4th assessment report. It says, warming of the climate system is unequivocal. For us, it was important to repeat it to basically establish a historic link to the preceding assessment report. For geoscientists, this is probably one of the most important figures when it comes to looking at changes of global nature. We did not put that figure in the summary for policymakers because we felt it was a little bit too complicated. It shows the change in energy content over the past 40 years. Since 1970, there are sufficient measurements of ocean temperature to allow us to determine the change in energy content that you see here. In the past 40 years, we had an increase of 250 times 10 to the 21 joules in the climate system. Most of it is stored in the upper ocean. That's the light blue part, the top 700 meters of the ocean. In the deeper ocean, we also see a temperature and therefore energy signal. And then there are 3 more compartments where we estimate the change in energy content. That is the cryosphere in white here, the soils in blue, in brownish colors here, and in dark red, the atmosphere. I show this figure because it displays and it demonstrates in a very nice way the physical importance of the changes do not lie with the temperature changes that we are used to consider in the atmosphere and everybody's talking about, but it's actually the energy change in the climate system, and that is stored and recorded primarily in the ocean as an increasing temperature worldwide, which you can then convert into an energy content. The change in energy content amounts to a tremendous number. It's 70 million terawatt hours that the planet has accumulated through the action of the greenhouse gas molecules and their increased concentrations over the past 250 years through the emissions caused by human activity. This number is 500 times larger than the annual consumption worldwide of energy. Of course, this is a curve and data that is very close to my heart because much of these data have been determined and measured at the University of Bern. It's the carbon dioxide concentration variations over the past 800,000 years from the Antarctic ice core from Dome Concordia, and it puts into a context the present day concentrations of carbon dioxide, the most important greenhouse gas after water vapor. I've combined the data from the ice cores, which you see here on the major part of this graph, with the direct observations from Mauna Loa that are available since 1958. And what you see is that, yes, CO2 has natural variations, of course. It varies with glacial, interglacial cycles, with high concentrations during warm phases, low concentrations during ice ages. But what we measure today is far beyond any of that variability and range that we determined from the ice cores over the past 800,000 years. In fact, it's 30% higher than any of these measurements that we have available in the ice cores. And therefore, the concentrations of carbon dioxide have increased to levels unprecedented in the last 800,000 years. That itself also one of these headline statements. This is another graphic that is important to keep in mind because it shows some further quantity that is unprecedented in the climate system. It shows the CO2 emissions in billion tons of carbon per year since 1980. And we see in 2013, once again, we have emitted a record amount of carbon dioxide into the atmosphere. At the moment, about 10 billion tons of carbon every year worldwide. And another number is quite interesting. Let's go back to 1992, the year which I refer to as the year when the legendary first Rio conference took place. Since then, we have increased the emissions by 61%. And you can argue 1992 was the point in time where the world has declared we have a climate change problem. All the governments have convened this Rio conference, and I take that as an expression of the knowledge that something in the climate system is happening. CO2 emissions by human activity are unprecedented. Let's now move to the second part of our assessment, dealing with the understanding. Here you see a comparison of the observed temperature increase. We are looking at the global mean surface temperature change since the end of the 19th century. These data are given as the red and the blue line, and as the black line. The red and the blue line show the multi-model simulations that are available for the fourth assessment report given in blue and the fifth assessment report given in red. You see that observations and model simulations of this global variable show quite nice agreement on the centennial timescale. They also exhibit all the major volcanic eruptions which cause a reduction in global mean temperature of a temporary nature. So just a few months to a few years, we see a reduction in global mean temperature. Now, if we perform the same simulations, but without increasing greenhouse gas concentrations, and without changing aerosol loading in the atmosphere, you see that only a part of the 20th century temperature evolution can be simulated in a consistent way. But in the last 50 years, the model simulations show a progressively increasing deviation from the observations. This is very evident here and is only one of the elements of knowledge why we can make a causal relationship between the changes in greenhouse gas concentrations during the 20th century and the changes in the physical variables that we see. Our assessment says that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. But this is not the only information that we have collected and assessed in our report. In fact, it's only one of many observations and causal relationships. So if schematically we plot the Mauna Loa curve as the cause here on the left side, we can then look at the worldwide effects, and there are many. We see warming in the atmosphere on land and in the ocean. We see changes in the statistics of extreme events. We see changes in the largest scale means of the water cycle over the 20th century. We also record changes in sea ice, shrinking of glaciers, shrinking of ice sheets. Some of the most impressive time series now come from satellite observations, where we can basically estimate the mass loss both of Greenland and Antarctica over the past 30 years. And finally, the most integrative measurement is global mean sea level, which has risen by 19 centimeters since 1900. The synthesis of all these changes and their relationship and dependence on the increase of greenhouse gases in the atmosphere has actually led us to make what is the shortest of these headline statements. We say human influence on the climate system is clear. And the power of this sentence is not that scientists have expressed that sentence, but the power is in the fact that this sentence is part of the government-approved summary for policymakers. This cumbersome process where we had to go through basically line by line with all the governments in the room, and the governments have approved this very sentence. Let us now move to the third part of our report, the future. Now for the future, we have only one choice in terms of scientific tools, and these are the comprehensive coupled climate models, the climate models that are basically representation of physical balance laws of momentum, mass, energy, etc. And these models are now used to project climate into the future. But you need a further element to do that, and that is you need a scenario. You have to make assumptions regarding the emissions of greenhouse gases, which are collectively taking into account the technological development, some assumptions regarding the development of the world, who will have access and how many people will consume energy and fossil fuel, and how that evolves over the 21st century. And what you see here is, just in a nutshell, these projections with respect to global mean surface temperature as we have them from simulations carried out by 25 centers worldwide, contributing over 40 different climate models, and from that huge amount of numerical data, over 2 petabytes of data has had to be analyzed, we extract information of that nature. You see on the left side the gray lines with a band depict the historical time period of simulations, which are then carried forward. Here, just for simplicity, 2 scenarios. A scenario in red, which is a so-called business as usual scenario. We call it the representative concentration pathway 8.5, because at the end of the 21st century we have a radiative forcing of 8.5 watts per square meter, taking into account all the different drivers in that scenario. And the second scenario, given in blue here, that you could call an aggressive mitigation scenario, a scenario in which we assume that carbon dioxide emissions will be reduced by a factor of 2 by mid-21st century, and in the second half of the 21st century, these emissions approach zero. For some of the simulations, they are even negative. That scenario will limit climate change to a certain temperature. You see here a temperature increase of no more than about 1 degree Celsius over the period 1986 to 2005. This means about 1.6 degrees Celsius over what we approximate to be the pre-industrial period, that is the last 50 years of the 19th century. Other scenarios have also been considered. They are given here as bars, as the means of the last 20 years of the 21st century. It's clear that based on these results, we can state that continued emissions will cause further warming and changes in all components of the climate system. Now, nobody lives in a global mean temperature, therefore we need to look at the regional distribution of these temperatures. Here I just show for the high emission scenario the last 20 years, a multimodal mean where you see warming in the range global mean of 3.7 degrees Celsius with enhanced warming over the continents, reduced warming over the ocean because of the tremendous uptake of heat by the ocean. You could say the ocean is rendering us a service, and in fact it's a double service. It not only takes up heat, it also takes up a huge amount of carbon dioxide, which otherwise would reside in the atmosphere or in the terrestrial biosphere. The biggest warming that these models project actually are in the Arctic. In the high latitudes of the northern hemisphere, you see purple colors which indicate warmings in excess of 7 degrees Celsius, which in this scenario lead to an ice-free Arctic in summer around the mid of this century. What is equally, if not more important, along with temperature, all other variables change that depend on temperature. This one here shows precipitation. The water cycle will change as well. In fact, we already observe some of the expected changes of the water cycle. And here you see a typical pattern of what we are expecting in the 21st century, in that the areas where we already currently have moist and wet conditions, for example, in the tropics and in the high latitudes of both hemispheres, you see bluish colors which indicate an increase in precipitation. So the wet areas get wetter. But the dry areas at the same time also get drier. So, for example, the Mediterranean areas, some areas of South Africa, Central America, Australia, all these areas where today we already have a shortage of water and drought stress, these areas will become drier. You could say that the hydrological cycle under global warming is accelerating, although this is ignoring a lot of physics. But our assessment says, in simple terms, the contrast in precipitation between wet and dry regions and between wet and dry seasons will increase. And it's important to see that it's not only a spatial change, but it's also a temporal change. The seasons will change, and this is crucial information for those colleagues who study impacts, who study biological impacts, who study the impact of physical climate change on ecosystems. Now, I mentioned the Atlas. I think this is a resource for you as well, because we make available all the model simulations and analyses of this Atlas publicly available in the form of numerical data in an easily accessible format, so-called NetCDF format, where you can extract the information already analyzed, so you don't have to go into 2 petabytes of model simulations. We analyze 35 regions over the world for 2 variables, temperature and precipitation, for 4 seasons and 4 scenarios. So you can see there's quite a lot of information there. Just by way of example here, the changes of surface temperature, we express that in percentiles to also give the flavor of a statistical analysis of these changes. We also provide time series. We do this for temperature and precipitation, and all that is available, for example, on this CD or directly on the internet. Now, let me come to another important insight that we could move forward to the policymakers. This is the Earth system, in very simple term, and sometimes you wonder how it's possible for the scientists to come up with very simplified global measures of what it means to increase carbon dioxide concentration in the atmosphere. Now, it turns out, based on many model simulations and theoretical consideration, that one quantity is really determining the global mean temperature change that we see in the 21st century, and that is the totality of all carbon dioxide emissions since the beginning of the industrialization. There is a nearly linear relationship between the totality of the emissions and the global mean temperature increase in the 21st century. It's like a metric, but it's not a metric that only looks at the physical aspect of the climate system, like the famous climate sensitivity, but it is a metric that also includes the carbon cycle response and the carbon cycle dynamics of the Earth system. This is called the TCRE, the Transient Climate Response on Cumulative Emissions. And in simple terms, it's the proportionality between the global mean temperature increase and the totality of all carbon dioxide emissions. And we can quantify that. About 1,000 billion tons of carbon emitted into the atmosphere since 1750 will cause a warming between 0.8 and 2.5 degrees Celsius. Now, you can immediately realize that this is of tremendous policy importance, because what it means is that a person or a society who decides to limit climate change and takes temperature as the limiting quantity, the quantity that you would like to have limited, then immediately by this proportionality, the total amount of carbon ever emitted is determined. And so we can say any climate target that society formulates or agrees upon implies a limited carbon budget. And this is, in my view, one of the most important messages of our assessment and of our message to the policymakers. And it took us quite some effort to get this new concept across to the policymakers, who finally and in the end accepted it. And this is the last figure in the summary for policymakers that basically encapsulates that new message. On the horizontal, we plot the cumulative total anthropogenic CO2 emissions since 1870. And on the y-axis, the temperature anomaly relative to that period. And you see all the simulations, and including the uncertainties, are basically covered by these 2 wedges here, these 2 clouds, a red cloud and a gray cloud. I don't want to go into the details here, but the simulations based on the 4 scenarios you see along these dotted lines that all lie more or less on a straight line, a proportionality between these 2 quantities, irrespective of the scenario. So the only distinguishing point of the scenario is actually when you reach the year 2100. So take the red scenario, you reach the year 2100 with a large cumulative amount of carbon and a large warming. Whereas in the mitigation scenario, which is given in the dark blue, 2100 is here because the emissions have been steadily reduced in the second half of the 21st century so as to limit the cumulative anthropogenic carbon emissions to less than 1,000 gigatons of carbon in total, which leads to then a warming of a bit less than 2 degrees. So the policy relevance of this figure is that the policymaker can go into this figure, identify his or her preferred climate target, for example 2 degrees, and then read off the total contribution, the total emissions of carbon dioxide since pre-industrial. For 2 degrees, it's about 800 billion tons of carbon. Now, taking this number, and here is the associated headline statement, limiting climate change will require substantial and sustained reductions in greenhouse gas emissions. Again, a sentence that is approved by all the governments, from Switzerland to Austria to the United States and Saudi Arabia. Everybody said yes to this statement. Now, let's take a few numbers here. 790 billion was the number that I quoted out of this diagram. Until 2013, we have emitted 535 billion already. So we are left with 255 billion, which are compatible with the 2-degree target. Now, this number is large, doesn't tell you anything if you don't put it into context of today, but you have that already in some of the previous slides. 10 billion tons of carbon emitted every year, approximately. So you can see it's about 25 years at present day emissions that we have left until we have missed the 2-degree target. And that's basically the physical scientists' formulation of telling the policymakers, hey guy, it's really urgent, but we don't say it in these words. Okay, so 2-degree world is this one here. Surface temperature changes by less than 2 degrees, with changes of more than 2 degrees over the continents, and even larger over the high latitudes of the Northern Hemisphere. There will be changes also in precipitation. We can calculate them, but they are hardly distinguishable from natural variability today. This is indicated with this hash pattern here on the map, which covers almost the entire planet. Important information for those who look at adaptation issues, means that ecosystems basically experience similar precipitation as they have dealt with already today. But nevertheless, this is a different world to which we have to adapt. Now, this world here is totally different. That's the world business as usual, 4.5 degrees warming, with enhanced warming over the continents, very strong warming in the high latitudes of both hemispheres. I haven't gone into sea level rise and many other quantities because of the shortness of time. Large changes in the water cycle, wet gets wetter, dry gets drier. This is a really different world, and Working Group 2 has looked at the question of adaptability of ecosystems and human systems, and they have concluded that in some regions, actually we will be reaching the limits of adaptation in such a world here. Obviously, since we are talking in scenarios, it's entirely our choice. It's our choice in which of these two worlds we are living. So that's in a nutshell what is in this 1,535-page document. All accessible to you in its last detail. Everything is on the internet on this address. And as I mentioned, you're very welcome to pick up a DVD here if you still have a DVD reader somewhere on your computer. Thank you very much for your attention.